All right. And our final speaker before the coffee break is Magdalena Larfors from Uppsala University. And she'll be talking about gauge two-form symmetries in 60 SCFTs coupled to gravity. Go ahead, Magdalena.
Thank you very much. So first, let me thank the organizers for the invitation to speak here. It's an honor. And what I will talk about is work together with Andreas Brown in Durham and Paul Konstantin Ullman, who is a postdoc here in Uppsala. And this was published earlier this summer in this paper here. So what I will talk about are, as Fabian just said, gauge two-form symmetries in 6-dimensional SCFTs coupled to gravity. So that's quite a lot of concepts in that title. So let me start with a motivation and a summary of this talk. SCFTs, so superconformal field theories, are interesting if you study quantum field theories, because these are fixed points for RG flows. So this has led to a lot of studies where SCFTs have been explored and classified in order to understand better what kind of quantum field theories there are. And this works in dimensions lower than 6 because superconformal field theories can only exist up to 6 dimensions. Now, in 6 dimensions, these superconformal field theories, if they're interacting, they are necessarily strongly coupled and they contain tensionless strings. So they are hard to study using QFT methods. However, from string theory and F theory, there is a way of engineering this that I will soon review. And this has led to a construction of a large number of examples of such theories. If you want to classify superconformal field theories, one of the things you should look at are the symmetries, because symmetries, as we all know, are preserved if you go down in, if you change the scale. So in particular on the RG flow, symmetries would be preserved. So if you want to use CFTs then to say something about quantum field theories, then you need to know something about the symmetries of the SCFTs. And in string and F theory, which will be the setting that we will be using here, these symmetries are related to geometry. So this has been used in the past to translate these questions into geometrical questions. Now in this talk, I will study a particular type of symmetry, which is a higher form symmetry, which is known to exist in superconformal field theories. And I will study what happens with this global discrete two-form symmetry as we couple the superconformal field theory to gravity. And in string F theory, what this means is that we should look at compactifications of these theories, which have SCFTs sectors. And I will soon tell you, or later in the talk, I will tell you what that means. What we will see in this talk and what I will argue happens is that the two-form symmetry that is present in the superconformal field theories has to be broken or gauged as we couple this to gravity. And this is because gravitational theories do not admit any global symmetries. And that includes also global higher form symmetries. And what I will argue is that whether the two-form symmetry is broken or gauged can be determined using lattice embeddings. So using tools similar to what Anna Maria used in her very nice talk that we just listened to. So by this, there is from this, the work that I've been doing, although it's on the formal side, there is some connection to the swampland problem. So sorry, to the swampland program. And we can, if we wish, view the study of how SCFTs can couple to gravity as a way of probing how quantum field theories can couple to gravity. So some way of studying the boundary of the swampland as opposed to the landscape. Okay, so higher form symmetries is something that has been studied for a long time now, but it might be good to review them quickly to make sure that everyone is on the same page. So let's start with an ordinary symmetry. So as you all know, an ordinary symmetry has, if it's If it's continuous, it has a one-form current, and from that we can form a conserved charge by integrating the dual of the current over a codimension 1 part of our space-time. We can view this, so either we can exponentiate this and we can get generators of the group. So this charge is related to the algebra, and if we exponentiate this, we get the group. But more abstractly, we can think about this as defining some sort of topological operator, which is related then to the kind of submanifolds that we are integrating this current over. And these topological operators are the objects that generalize to any kind of symmetry, be it discrete or continuous. So in a discrete symmetry, we do not have a current because there are no infinitesimal changes. So associated to this topological operator, there is a group law which one can derive, and this then encodes the multiplication law of the group. Furthermore, these topological operators couples to charged local operators of the theory, which in this case would be then particles, so zero form operators. And the way that it couples is that we can surround the local operator with a sphere and look at the topological operator on that sphere. And then this will correspond to this will pick up the charge of the, or the representation of the operator under the group. So this is this kind of equality can be written down. So we can generalize this, and this was done in 2014 by Gayotta, Kapustin, and Siberian Village, to p-form symmetries, where if we have a continuous symmetry, would replace the one-form symmetry, the one-form current with a p+1 form current. And we can then integrate that and get conserved charges. More generally, we can talk about these topological operators, which will now then be related to submanifolds of codimension p+1. Similar to the ordinary case, the ordinary symmetry, the zero form symmetry, we have this group law, and we can look for these charged operators by looking at how these topological operators can link with various p-dimensional local or semi-local operators. So if you have a p-form symmetry, you have these p-dimensional operators, and that is the things that you should look for if you want to find a p-form symmetry. So since what we're interested in this talk are the two-form symmetries, what we will look for in our theories are surface operators. Okay, I already mentioned that six-dimensional superconformal field theories are known to have two-form symmetries. So how can we see that? Well, one way of seeing that is to use type 2b string or F theory. And we can do in this theory, we can engineer a six-dimensional superconformal field theories by putting the 2b string or F theory on two-dimensional spaces, which are non-compact in order to decouple gravity, and which has this particular form. So it's C2 modeled out by some group in U2. Now, if we look at the compact cycles, two-dimensional submanifolds of this, so complex one-dimensional, one complex dimensional, two real dimensionals, cycles in this space, we can wrap D3 branes in the type 2b string on this, and that will leave us with a string in 6 dimensions, or one-dimensional object in 6 dimensions, or 1 + 1 dimension. So if this is a compact cycle, this will give us the string, and if it's a non-compact cycle, it will give us a defect in the 6D theory, that is a non-dynamical object. We can also engineer gauge and flavor groups, although this will not be very important for this talk. And in F theory, all this can be encoded as an elliptic fibration, as is well known. Now, the strings and the defects are key here to the two-form symmetry, because as I just said, we're looking for these surface operators. So what one can see is that if you think about the six-dimensional space-time as being Euclidean, these defects will actually give rise to two-dimensional non-dynamical operators, so surface operators. And what defines the theory that we get, or what kind of two-form symmetry we get, is specified by the charges of these dynamical strings that we have and the defects and surface operators. And these, the charges of these are specified by certain lattices. So here's where the lattice come in. And the lattices has an inner product which is determined by the intersection of the cycles that the D3 brane wrap in this type 2b picture. So what happens in the six-dimensional theory is that these dynamical strings, or the D3 branes, they can be dynamical, or at least if we go to special points in the moduli space where they become light, then they become dynamical and they can screen these defects. And this means that they will break the two-form symmetry that the defect is charged under. So as long as we have these dynamical strings, there will be some at least partial breaking of the two-form symmetry. It was shown by Badwai and Shatanomeki some year ago that unless the charge lattice then is self-dual, since the charges of the dynamical strings is given by lambda s and the charge lattice of defects given by the dual of that. So unless this is a self-dual lattice, there will be a global two-form symmetry remaining, but it will be discrete and it will be determined by this, this lattice quotient. So this is, of course, the same object that Anna Maria was talking about in her talk. I should also mention that this group here is also known as the defect group because it's associated to the defects in the six-dimensional theory. And this relates to a curious property of the six-dimensional SCFTs, which is that they are relative theories. So you have to specify a background three-form flux before you have completely specified your theory. So the two-form symmetry is something that you need to specify to completely know what theory you have. Now, if we now want to couple this to gravity, we should see if we can include these SCFT sectors in gravitational theories in some way. So what we should do then in the type 2b or F theory picture is that we should try to compactify this two-dimensional surface that we have, this two-dimensional space that we have compactified, that we used to construct the SCFT. So let's start then by thinking about how the six-dimensional supergravity work, where you now have type 2b string theory on a two-dimensional space, which is compact. So there will still be an intersection lattice that comes from compact cycles on this space. And if I'm, I would be interested in the ones, sorry. And this will be given by the second homology or second cohomology, and that takes values in the integers. I can still put the three branes on these cycles, and this will give to, in general case, massive strings in 6D. But if I go to special points in the moduli space, where the volume of the cycle shrinks, then I will get tensionless strings. So what I can see is that as I go to special points in the moduli space, there will be SCFT sectors emerging, which are specified by certain sublattices of this lattice of compact cycles that are shrunken. So if I want to see if an SCFT can be coupled to gravity, I need to explore whether I can fit the charge lattices of the SCFT into the lattice, the cycle lattice of a compact base. And since there are infinitely many six-dimensional SCFTs, if you allow the rank of the gauge group to go up, but only finitely many bases for Calabi-Yau threefolds, you would expect that this is not always possible. Furthermore, we know from the last slide that each SCFT sector has its own two-form symmetry, which is global if we zoom in on that SCFT sector. But we also know from quantum gravity law that global symmetries should be absent. So then these two-form symmetries must be broken or gauged. And the question then we want to answer is whether they are broken or gauged. So first things first, if we look at six-dimensional supergravity and we look at the full string charge lattice, it has been shown that this is self-dual. So there cannot be any point where all of the apologies, where all of these where there is a global two-form symmetry, simply because this is self-dual lattice. But there can be it can be possible to gauge part of this subgroup. And what I will explore here is what happens to these BPS strings that comes from D3 branes. So it's a caveat here that I'm not, there might be other strings or other objects that could screen this two-form gauge group, and that I don't know of. So there's certainly some more room for exploration there. Okay, so what can we do? So in order to construct then this coupling between SCFTs and supergravity with either 2,0 or 1,0 supersymmetry preserved in 6 dimensions, what we do is we take a type 2b string theory or F theory on a compact 2-dimensional space with a given string lattice, and then we choose a sublattice in that lattice. We explore the SCFT sectors that emerge if that sublattice is shrunk to at some point in moduli space. And then we can determine the two-form symmetries of these SCFT sectors, and we should and what we should look for is if there is some subgroup of the putative two-form group, which is under which these strings are invariant. If that's the case, then the strings cannot screen that part of the group, and that will remain as an unbroken gauged subgroup. So put more into lattice theoretic words, what you then want is that there should be an element in the dual lattice, the dual string lattice, which is not in the string lattice, but which, when we multiply it by some integer, should be in the lattice. So since the dual lattice is has the possibility of having fractional lattice components, this is indeed possible. But we also need to check that this remains when we intersect the string lattice with the lattice of the compact base. So what one can show, since these kind of elements that I'm talking about here, they are torsional elements, they're known as torsional elements. So what we need to check then is if the torsional subgroup of that is given here is non-trivial. So what we find then is that the SCFT sectors that are specified by lambda s, they preserve a gauge two-form symmetry if the lattice lambda s is non-primitively embedded in lambda b. And being non-primitively embedded means exactly that there are these kind of components in lambda b that are not included in lambda s. So now I've talked a lot about the generalities here, and we have about 5 minutes to go. So I will talk about how this looks in examples. So first, let's look at a 1,0 supergravity example. So here I will start, if I want to preserve 1,0 supersymmetry, I should look at F-theory computations on some which has an orbifold base, or which has some base, and I need to look at this from the perspective of F-theory, because with 1,0 symmetry, I can have D7 branes in the picture. And these then require a non-trivial vibration. So the base of this vibration will be an orbifold, which I pick to be P2 over C5. And this I can encode in a toric diagram with 3 rays, which look like this. So this is now an orbifold, so it's a singular space. So if I want to find the SCFT data that goes with this, then I first need to find the exceptional devices in a minimal resolution of this space. So these are drawn here in black. And I also need, if I want the full SCFT data, I need the gauge groups that are associated to these resolution rays. So with these resolution devices, the base becomes smooth, but something funny is happening in the fiber, and I get these enhanced gauge groups. So the SCFT data in this example is then that we have these these exceptional devices and associated gauge groups with them. So we have an A4 here, and then there are 2 non-Higgsable clusters with these -2 and -3 curves. And if we look at this and we compute this, what the 2-form symmetry that is preserved then by these resolution, by strings wrapping these resolution devices, we find a Z5 form, 2-form gauging. And if we go to the tensor branch of the theory, we can also read off this Z5 gauging using toric geometry. So what we can see explicitly is that there are linear relations between the curves, simply because there are more curves in than you need to for the 2-dimensional for this to span this 2-dimensional lattice. So there will be linear relations, and one such relation is shown here, where we see that these original devices that I started with here, which correspond to the vertices V1, V2, and V3, they have a relation with a 5 in them. So 5 times the x1 devices minus the x2 devices is given by a sum of resolution devices. So as I go to the point where I blow down all of these exceptional devices, then this will become a torsional element. And if we should preserve this relation, then the strings may only wrap curves, which are these resolution curves, which have a product with this D5 devices, which is 0 mod 5. So this is then a way of seeing the Z5 gauging. We can also, so that was a 1,0 example, and one can do a similar analysis in 2,0 supergravity. Here there is more supersymmetry, and there's a very nice connection to model Y groups and the torsion of model Y groups. So what one can show in complete generality is that if the K3 surface that we need to compactify type 2B string on to get a 2,0 theory, if this is elliptically fibered, then the 2-form symmetry group that we get will be given by the torsion part of the model Y group. So we can then use, so what's nice about this is that a lot of things are known about the model Y groups of elliptic vibrations, and we can then use that to explore gauge 2-form groups in 2,0 supergravity. And here is an example of a simple Weierstrass model that engineers a Z2 2-form, Z2 2-form gauging. Now I should say that if X is not elliptically fibered, so if we have a K3 and we choose a duality frame where this is not elliptic fibered, then there are other ways of engineering these 2-form gauge symmetry groups. And the mirror quartic is one example where you can find both types of two-form gauge groups. Before I conclude, let me mention that you can get support for the idea that the two-form the part of the two-form symmetry group that is not broken by BBS strings is indeed not broken, but remains as a gauge group from duality. Yes.
I mean, I know you said you will conclude. I just want to point out that you're running into your question time.
Yes, I know. So I will just say here that there is a nice argument from duality that relates this, from duality and circle reductions that relates the results that we have found to known results about one-form symmetry groups in 5 dimensions, and also results about 8-dimensional theories from F0 on K3, so very much related to what Anna Maria just talked about. So with that, let me conclude. So I've told you that 6-dimensional SCFTs have global discrete two-form symmetries. And when coupled to gravity, these two-form symmetries must be broken or gauged. I have argued that they will be gauged or for them to be gauged, we need the charge lattice of the string to embed non-primitively in the string lattice of the base, the compact base, and this can be expressed in this formula here. So the two-form symmetry group that we get is given by the torsional part of lambda b over lambda s. And this applies to 1,0 and 2,0 supergravity. It also applies to little string theories. One can ask the question whether this group is broken by other effects, but at least in examples, we can see that duality supports that it's not. So of course, there are things that one can think about doing with this. So one possible way forward is to look at dimensional reductions of this theory. There is definitely need to analyze the field theory further and look at anomaly cancellations. And more generally, one can ask what the allowed two-form gauge groups are in 6-dimensional SCFTs coupled to gravity. And with that, I conclude. Thank you.
All right, thank you very much, Magdalena. Other questions? Yes, there's a raised hand by Morty.
Yeah, thanks, Magdalena. That was a really nice talk and very interesting stuff. I have a question for you. So you've used the primitivity of the embedding as a criteria for figuring out what happens to this two-form symmetry. So I guess I have 2 related questions. One is, once you've figured that out, can you then turn that into some kind of intrinsic statement you can make about the theory? And related to that, do you know of any cases where you can actually have an embedding of the same theory where one embedding is primitive and the other one is not, which would actually say that the answer to my first question had to be no?
Yes. So so let me start with the second question, whether this depends on the so whether I can take one SCFT and with a related charged lattice then and embed it in different ways. That is certainly true. So one can it's not a unique embedding. So one can think of different ways of coupling SCFT sectors to gravity. And,
right, I guess the question is, if there are different embeddings, can they sometimes have the feature that one is primitive and one is not? Or in other words, is the primitivity an intrinsic feature of the 60 SCFT?
So I haven't explored it, so I don't know. So I don't really know. It's an interesting thing to explore.
Thanks.
I think the answer might be no, because even in the limit where the CFT is decoupled, you could add some like background tensor multiplets to make the original defect group trivial. So
right. So of course, what we're talking, yes. So this is a very good point. So in order to make progress here, what we wanted to do was to define some sort of minimal setting where we are exploring these questions. So there are, I mean, one can think of resolving a theory further, and I think that would change the conclusion.
Okay, thanks. Nice talk.
Jonathan, do you have another question, or did you just want to make this comment?
No, I had another question. So you focused mainly on the case of two-form symmetries. How about the interplay with one-form symmetries? So for example, when you take one of these SCFTs that has an ordinary kind of zero-form global symmetry, you're going to gauge that one as well. And you might imagine that there's then also some mixture between, well, not just anomalies for two-form symmetry, but also with one-form symmetries and so on.
Yeah.
So
it's a really good question, and we haven't explored it at all. But I agree, it would be a very good thing to look at.
Did you have a guess for what the generalization of, so in your boxed equation, you talk about this embedding of a torsional piece of lambda b over lambda s. Is there a guess for what it would be if you now include the pieces from the gauged groups?
I don't have one, I'm sorry.
Okay, thanks.
Okay, then we end it here. Let's thank Magdalena again.
Thank you.